Every single time you shop online or send an email or even just browse a website, there's this invisible force field protecting you. And that force field, well, that's cryptography. Today, we're going to pull back the curtain and show you exactly how it all works. So first, we have to understand the basic problem with the internet itself. See, sending any piece of information online is kind of like sending a postcard. As it travels from point A to point B, literally anyone along the route can just pick it up and read the whole message. Not exactly private, is it? And that really leads us to the big question, right? How on earth are we supposed to have a private conversation or a secure transaction when all our messages are basically out there in the open? How do we turn that flimsy little postcard into, say, a locked, tamper-proof briefcase? Well, the answer is cryptography. It's the science, really the art, of scrambling messages so that only the person who's supposed to read it can unscramble it. It's what gives us the digital locks and keys that are the absolute bedrock of our modern connected world. So what does cryptography actually do for us? Well, you can think of it like this. Every secure system makes 3 fundamental promises to you, the user. Let's break down what those are. In the cybersecurity world, they call these promises the CIA triad. First, there's confidentiality, which is the promise to keep your data secret, a total lockbox. Second, you've got integrity, which guarantees your data hasn't been secretly changed or messed with. And third, there's authentication, which proves that the person or website you're talking to is actually who they say they are. Cryptography is what makes all 3 of these promises a reality. Now, to deliver on those promises, cryptographers have a toolkit with 3 main tools. It's best to think of each one as a different kind of lock, designed for a different kind of job. So let's open up the toolkit. Okay, our first tool is called symmetric encryption. This one is the most straightforward of the bunch. Just imagine you have a lockbox and one single key. You use that key to lock your message inside, you send the box to your friend, and they need that exact same key to open it up. Simple. The real beauty of this method is just how simple and fast it is. The exact same secret key is used to lock it up and unlock it. This makes it perfect for encrypting huge amounts of data really quickly. But it has one giant problem. How do you get that secret key to your friend in the first place without somebody else intercepting it? And that key sharing problem? Well, it brings us to our second and honestly very clever tool, asymmetric encryption. This method solves the problem by using not one key, but 2. This is where the genius of the system really kicks in. Everybody gets 2 keys that are mathematically linked. A public key, which you can give out to anyone and everyone, and a private key, which you protect with your life. So anyone can use your public key to lock a message and send it to you, but only your private key can unlock it. It's just like having a mailbox with a public slot for dropping letters in, but only you have the key to open the box. So let's just quickly put them side by side. Symmetric uses 1 shared key. It's super fast, but it has that tricky key exchange problem. Asymmetric uses 2 keys, 1 public, 1 private, which is a bit slower, but it brilliantly solves the problem of how to start a secure conversation with someone you've never even met. All right, now for our third tool, which does something completely different. Hashing. It isn't about hiding a message. It's about proving a message hasn't been changed. Think of it like a tamper-proof seal on a medicine bottle. So here's how it works. A hash function takes your data, any data, could be a single word, an entire book, a movie file, anything, and it runs it through a special math algorithm. What it spits out is a unique string of letters and numbers, called a hash. And here's the magic trick. It's a one-way street. You can't turn that hash back into the original data, ever. The perfect way to think about this is like a digital fingerprint machine. No matter how huge the input file is, the output, the hash, is always the same short length. And here's the cool part. If you change even a single letter in that input, just one tiny character, you get a completely different fingerprint. This is how we can guarantee that data hasn't been tampered with. And right here, this is the big aha moment for how this gets used every single day. When you create a password for a website, they don't store your actual password. No way. They run it through a hash function, and they often add a random bit of data called a salt just for extra security, and they store that final hash. So when you log in, they do the same thing to the password you just typed and just check if the fingerprints match. This way, even if a hacker steals their database, they don't get your password, just a useless jumble of text. Okay, so we've got our 3 tools in the toolkit. How do they all work together? Let's look at the most common example you see every day, that little padlock icon in your browser bar, HTTPS.
So when your browser connects to a secure website, they do this little dance called a secure handshake. First, they use that slower but safer asymmetric encryption, the whole public and private key thing, to prove who they are and securely agree on a brand new one-time use key for symmetric encryption. Then, for the rest of your visit, they switch to that much faster symmetric key to encrypt all the data. It's really the best of both worlds. You get the security to start and the speed to continue.
It's really easy to see all this as just, technical jargon, but I can't overstate how important this is. Cryptography is the fundamental bedrock of all digital trust.
Seriously, just take a second and imagine a world without it. You couldn't safely use your credit card online. Your private messages would be public knowledge for anyone to see. Your bank account would be completely exposed. The internet would just be this chaotic Wild West where every single thing you do is a massive gamble.
And that really brings us to our final, most important takeaway. It is absolutely not an exaggeration to say that this complex, invisible science is the single thread holding our entire digital society together. It's not just about protecting data. It's about making trust possible in a world of digital postcards.